Hi team, welcome to Wiggins Maths. In this video we're going to be looking at problems where you are asked to find the area or the area bound between two functions. Now, I'm quite looking forward to this one because you get to see my wonderful art skills. I'm sure you'll be thoroughly impressed. But before we get to that, a polite reminder to not neglect the formula booklet. Okay, so let's just review what we already know. Told you my art works great. If we wanted to find this area R, we would be integrating y with respect to x between the limits of b and a, or to put it another way, be integrating between b and a of f of x with respect to x. So that's what we already know. Okay, so what about if we wanted to find the area of R1? Well, this time it would be the integral between c and b, and it would actually be g of x subtract f of x. So if the function is the one that is above, that is what we start with, because if we think the integral between c and b of this function would give us this whole area here, and we're going to take off the area underneath this blue curve. So if we subtract those two functions, then that will do the job for us. Likewise with the region R2, that would be the integral between b and a in this case, and this time it is going to be f of x subtract g of x with respect to x, because the blue function is now above the purple function. Okay, so let's start off with this then. So very similar to a year 12 question, but very much a year 13 function. So here, let's just set it up. We are going to integrate between 2 and 0, 3 over 1 plus 4x to the power of a half dx. So firstly, I'm going to rewrite it like this. And secondly, I'm going to remove this 3. I'm going to take that 3 out, because I can do that when I'm multiplying a whole thing by 3. And that means it's going to leave us with this. So we get, when we integrate this, so it's going to be 3 lots of, and then when we integrate this, it's going to be negative 1/2 of 1 plus 4x to the power of a half between the limits of 2 and 0. So this is 3 lots of, and then if we substitute in our correct values, so that's 1 plus 4 lots of 2 to the power of a half, subtract okay, and we end up with 3 lots of 1, which is 3. Since it's the area, we should put units squared really. Okay, so same idea, showing you that to find the area, it's just a slightly more complicated function, but we can deal with that now. Okay, so this one is where we are finding the area between two functions, between two curves. So this is going to be the integral between pi over 2 and 0 of f of x subtract g of x with respect to x. Okay, so let's put those in. So f of x is sine 2x subtract sine x cos squared x respect to x. Okay, so let's look at integrating each of these terms. So sine 2x is going to be something to do with cos 2x. So if I pretended it was cos 2x, if I differentiated that, it would become negative 2 sine 2x. So I need to take a negative 1/2 of that. And then sine x cos squared x, this second term differentiates to give this first term. So I'm going to try cos cubed x. And when I differentiate this using the chain rule, I get 3 sine x cos squared x. So I need to take a third of that between the limits of pi over 2 and 0. And then when we chuck in those values, and we have to be a little bit careful here. So we're going to chuck in pi over 2 first. So cos pi over 2, add 1/3. Plus 1/3 cos cubed of 0. Okay, and when we evaluate this, we will get 1/2 from this bit, and it's going to be negative 1/6 from this bit, so we're going to add 1/6, so it is 2/3 units squared. Okay, and our third and final example is a bit tastier. Okay, so it looks like it's just a normal curve, but it has been parametrized. So we've been told what x is, what y is. We've been told some certain restrictions on t. We've been told a particular coordinate. So it tends to be a scaffolded question, which is good news for us. We're not left to just sort of fight for it. Okay, so we're going to look at each of these parts individually. So let's have a look at part A. Find the value of A, so the coordinate A, 4. So the y coordinate is 4. So let's just work this out. Now, of course, sec is 1 over cos, so therefore this must be true. And a reminder that we are being super careful here and making sure that we are in radians, not degrees. So t is pi over 3, and if t is pi over 3, then x, we want the exact value, is 3 pi over 3 sine pi over 3, which is sine pi over 3 is root 3 over 2, 3 pi over 3 is pi, so it is pi root 3 over 2. Okay, so we have that value of A. Now, often students get to this sort of question, I show that question of this form and panic a little bit. Firstly, let's have a look at those limits. So pi over 3. Pi over 3 was the value of t at this point here. So at this point here, t was pi over 3. So that seems pretty reasonable. Right. Also earlier I reminded you that the area under a curve is y dx, right? Between the limits, in this case it's going to be a and 0. Now, how could we make this so it is dt? Well, what we can do is we can change those limits to pi over 3 and 0, and we can say that this must be the same as this. We think the dt's will cancel each other out, leaving us with y dx. So if we take x is 3t sine t, we can work out dx by dt. Now this is going to have to use the product rule, isn't it? Okay, so that's going to be 3 sine t add 3t cos t. So now we can actually rewrite this integral as the integral between pi over 3 and 0 of y, and y was, I'm going to write it as 2 over cos t, so that's 2 sec t, wasn't it? And then that's going to be multiplied by 3 sine t plus 3t cos t with respect to t. So we're nearly there. It might not look like it, but we're nearly there. If I was to expand this out now, I would get 6 sine t over cos t plus 6t cos t over cos t. And then we're really nearly there now. So we can take out that 6 because it's multiplied throughout by 6. And then sine over cos is tan. And then cos over cos cancel each other out, leaving us with just exactly what we wanted. Which is lovely. We've got there. Now, it's also worth pointing out, since this is a show that question, we can still do part C even if we struggle to find part B. I'm going to do part C now. So 6 of tan t plus t dt, and that is equal to 6 lots of the integral of tan t is in the formula book, remember, so sec t plus t squared over 2 between pi over 3 and 0, and then there's this little faux here, exact value. So if we were to try and type this into our calculator fully, your calculator isn't going to do the trick for us here. So we may have to do it a little bit more manually. So it's 6 lots of ln sec pi over 3 plus pi over 3 squared over 2 subtract ln sec 0 add 0 over 2. Okay, so that is 6 lots of, well, sec pi over 3 is 2, so it's ln 2. Okay, because cos pi over 3 is a half, so sec pi over 3 is 2, plus it's going to be pi squared over 18. And then subtract ln sec 0, cos 0 is 1, ln 1 is 0, plus 0 is 0. So we're nearly there now. So I need to multiply everything by 6. We're going to get 6 ln 2 plus pi squared over 3, and then that is units squared. Whew. So those are really our 3 different example types. Curves, slightly more complicated, between 2 curves, and a parametric form. Okay, as always, if you found the video useful, please subscribe, tell your peers, and I will be aiming to upload new videos each week to ensure that we are as successful as possible. And of course, amateurs call it genius, masters call it practice.